Hi, in this video we're going to be doing a thermochemistry review. So first it says a 85.2 gram copper bar was heated and placed in a coffee cup. The final temperature was 26.15. How much heat was gained? Alright, so to find this, how much heat is gained by water, we use Q equals mCp delta T. Alright, so it will be the mass of water, which is 425.01 ml. 1 ml is approximately equal to 1 gram. So, because the density is 1 gram per milliliter. So this will be 425 ml, aka grams, times the Cp of water, which is 4.164, which will be given. And then times that by the changing temperature. What is the changing temperature? It starts from 22.55 and ends at 26.15. So 26.15 minus 22.55, and we will get number 425 times 4.164 times 26.15 minus 22.55. We get 6217 joules, about 6220. So the second one, how much heat was lost by the copper? Well, the heat lost by the copper is being gained by the water. So the heat is going to be the same, 6,220 joules. 6,220 joules is lost by the copper to be gained by the water. Now, what is the specific heat of copper? Okay, specific heat of copper, we're going to use Q equals mCp delta T, where we're looking for Cp. Our Cp is going to be equal to Q of Cu divided by m delta T. Q of Cu we found in this part B as 6220 joules divided by mass, which is 85.2 grams, times the change in temperature, which is 26.15 resulting temperature, minus the initial, which is 221.32. Alright, so let's see what that is. 6220 divided by 85.2 times 26.15 minus 221.32. And we will get 0.374. And this will be joules per grams degree Celsius. And for part B, again, this is 6,220 joules of heat lost, or you can rewrite it as negative 6220 joules lost. But since the question will ask you how much was lost, that's why I kept it as 6220. Now, D, was the energy conserved in the process? Well, the answer is yes. All of the heat lost by Cu was transferred to the water. And I think every single time you see a question where it says was energy conserved, I think the answer will always be yes, unless there are some weird exceptions in the problem, because energy should always be conserved. Next, a 100 milliliter sample of 0.676 molar of HCl. Calculate the enthalpy change delta H reaction for the formation of 1 mole. Okay, so delta H reaction is equal to Kj divided by mole. So we need to find the delta H reaction. So Q solution is equal to 200 grams mCp delta T, 4.184 for water, and the changing temperature will be 28.2 in the end, minus the initial, which is 23 degrees. Okay, now to put this in our calculator, 200 times 4.184 times 28.2 minus 23 will get 4351 equals 43550. Let's round to 50 joules. Alright, because Q reaction from a few minutes ago, Q reaction is equal to negative Q surroundings, our 4350 will become negative 4350 joules. Now we gotta calculate the moles. Let's create an RBCA chart of H plus OH minus forming H2O. We have how many moles? First, 100 grams divided by, no, multiplied by 0.76 molar, 0.1 liters times 0.76 molar, which is 0.076. And the OH is the same thing, which is also 0.076. And the water, we start off with 0. So minus 0.076 on both sides, and plus 0.076. So we're going to have 0.076 moles of H2O. Now, since delta H reaction is kg divided by moles, we can use this number divided by moles, which is 0.076. Negative 4350 divided by 0.076 is equal to negative 57,237 joules per mole. Now, since we need kJ per mole, we need to divide this by 1 kJ by 1,000 joules. So divide that number by 1,000, and we'll get our final answer of negative 57.2 kJ per mole. And that's our answer for part A. Is the reaction endothermic or exothermic? The answer is going to be exothermic. Was the energy conserved in the process? Yes. Heat lost by reaction is gained by solution. Our number 3, it says we have 100 milliliters of 1.5 molar BaNO3 and then we are adding 100 milliliters of 1.50 Na2SO4, and a precipitate forms and temperature rises and density of solution is 1 grams per milliliter. The reaction could be represented as a complete ionic or net ionic equation. Write the net ionic equation. So net ionic equation will remove anything that is a spectator ion, which is a weak conjugate. HNO3 will be a strong acid, so NO3 minus is a weak conjugate base, and same goes for Na. So our net ionic equation will be Ba2 plus aqueous plus SO4 minus aqueous, making BaSO4 solid plus heat. Find the amount of heat that was lost or gained. So we can see here the temperature rised, which means the reaction lost heat. The reaction released heat into its surroundings. Okay, now first let's combine these liquids. We have 100 milliliters plus another 100 milliliters, which is 200 milliliters. And the density is 1 gram per milliliter. So for every 1 gram, we have 1 milliliter. And this will be equal to 200 grams. And our Q is equal to 200 grams times 4.184 joules per grams degree Celsius, which is Cp, times 29.7 after temperature minus initial temperature, which is 25 degrees Celsius. Now if we do all of that, 200 times 4.184 times 29.7 minus 25, we get 3,930 joules. And this is rounded to 366. And this is the amount of heat that was lost. Heat lost. Because again, our temperature increased. And now we need to find the delta H. So first, let's calculate the moles. All right. Moles, again, kJ divided by moles is equal to our delta H. That's why we need to find the moles first. Moles is 1.5 molar times 0.1, which is 0.15 moles of Ba2 plus. And since it's the exact same thing for SO4, which is equal to moles 0.15 moles of SO4 minus. Now let's do a RBCA chart of Ba2 plus SO4 minus, forming BaSO4. This is going to be 0.15 on both over here. Now it's going to minus 0.15 into 0. This is going to be 0 initially, plus 0.15, and it will turn into 0.15. Now that we know we have 0.15 moles, we can do negative 3930, because this is energy lost. Energy lost is negative joules divided by 0.15 moles. And since we're looking for kJ per mole, we're going to convert it to 1 kJ for every 1,000 moles. Because delta H is always calculating in kJ. So that's why we need to divide by 1,000. So negative 3930 divided by 0.15 divided by 1,000 is going to give us negative 26.2 kJ per mole. That is our delta H. Now, is this endothermic or exothermic? It is exothermic. Because again, we're releasing heat and our heat delta H reaction is negative. Now for an experiment, 1 mole of ice at 0 degrees become 1 mole of water at 0 degrees. The enthalpy change associated is referred to the heat of fusion of ice. In the experiment, a 9.68 gram sample was added to a coffee cup containing this much distilled water. The temperature was this before, and the lowest temperature that recorded is 19 degrees. Find the heat lost or gained by the water. Alright, so let's see what we do here. First, we do water. Q of H2O is equal to mCp delta T. How much mass we have? We have 278.25 water. So 278.25 grams, because water density is 1 gram per milliliter. And it's going to be, multiplied by Cp of water, which is 4.184 joules per grams degree Celsius, multiplied by the changing temperature, which is 19.050 degrees Celsius after, and 22.485 degrees before. This will give us, let's see, 278.25 times 4.184 times 19.050 minus 22.485. We get negative 3,999. And this is going to be joules. In this experiment, the ice melted when the temperature of the water produced by the ice increased from 0 to 19. Calculate the heat absorbed by the ice, Q melted ice, as the temperature increases. Alright, now this time we're just solving for Q, and it's for ice this time. So Q of H2O is still equal to mCp delta T. Except this time we have 9.68 grams of ice. So it's going to be 9.68 grams times, it's still going to be 4.184 joules per grams degree Celsius as our Cp, which has specific heat for water. And over here, the temperature is going to be 19.050 minus 0 degrees Celsius. And this is going to be 9.68 times 4.184 times 19.050, which will be 772 joules. Calculate the amount of heat that was gained by the ice. So this time it's Q melting. So Q melt plus 772J is equal to negative 3999 joules, because again Q of system is equal to negative Q of surrounding. So we negative the already negative 3999, which makes this a positive. So 3999 joules positive. So it's 3999 minus 772, which gives us 3227 joules. Q of system equals negative Q surroundings is a very important concept that you need to remember. And finally, calculate heat fusion of ice, which will be delta H first is equal to 3227, as we found in the previous one, 7 joules, divided by our mass, which is 9.68 grams, which will be equal to 333 joules per gram. Now, is the reaction endothermic or exothermic? The reaction is endothermic because our temperature went down. It went from 22 degrees to 19 degrees. So therefore, it is endothermic. And the reasoning is because the temperature of our surrounding went down. Energy was transferred from one system to another during the experiment. Identify the two interacting systems and outline the direction of energy flow. So let's see. This is going to be a system. And everything else, let's call this the surroundings, right? And the energy flow is going inside the system. And was the energy conserved in the process? And the answer is yes. Heat flowed from the water to melt the ice and reach equilibrium. Number 5. How much heat is released when 24.8 grams of CH4 is burned to excess oxygen gas to produce carbon dioxide and water? So let's see here. 24.8 grams of CH4. 1 mole of CH4 has how much grams? C plus 4 H's will be 16.642 grams of CH4. Now, from the moles, we go 1 mole in every reaction for one reaction, and then for one reaction we have negative 800.3 kJ. Whoops, sorry. This is negative 800.23 kJ per mole. So instead of writing one reaction up here, we'll write negative 802.3 kJ, because this is kJ per mole. So now we do 24.8 divided by 16.642 times negative 802.3. We'll get an answer of negative 1200. And our answer will be negative 1196 kilojoules. Let's see, 1196 kilojoules, and we'll round to 4 sig figs because we're given with 4 sig figs over here. How much heat is released to absorb when 45.8, so this time it's 45.8 grams of hydrogen gas, it's H2, and 1 mole of H2 is 2.016. And then for every one reaction, there are 3 moles of H2, and it's negative 92.2 kJ per mole. And let's see, 45.8 divided by 2.01 divided by 3 times negative 92.2. We're going to get an answer of negative 698 kilojoules. Over here, we're given 3 sig figs, and that's why our answer is 3 sig figs as well. And I know I haven't been paying attention to my sig figs early on, but from now on, I'll be watching out for my sig figs and trying to round it to as what we're given in the question. And that's it for this thermochemistry review. Thank you for watching.